Last but not least, we have Jannik Mähn, who is a second-year PhD student diving into the formal verification of cryptographic protocols. And his research is about proving the semantic security of TPM-based remote attestations. And let's get into more.
Thank you, Ms. Omar. So we made it to the final session of this workshop. And we're lucky because some of my content has already been presented, so I can make it a little bit quicker. So my name is Jannik, and I'm going to talk about formal verification of TPM-based remote attestation. As already said, I'm a PhD student in the trustworthy data processing group of the Barkhausen Institute. And very quickly about us, we are from Dresden. We are a rather young institute with a vision of providing trustworthiness to the Internet of Things, where formal verification, of course, is a crucial part of. And my topic is formal verification of cryptography and cryptographic protocols. And I use the SSProve library that has been mentioned already before, which is based on COC. Okay, the project or motivation, I guess I don't have to tell you what remote attestation is. So the question is, why do we want formal verification? So if you look at the TPM specification, you see it's a really big file of C pseudocode. And the TPM does provide many functionalities, including cryptography. And when I look at the cryptographic protocol, I would like to see some statements about correctness and security. And when I talk about security, I'm usually referring to semantic security rather than more protocol-based security, as many email attacks. And since the specification is underspecified, we want to apply formal verification. And we use the SSProve library because it does exactly provide means of talking about semantic security. And the idea is, or the idea behind SSProve is essentially state separation proofs. That's where the SSP comes from. And this is a very common methodology in cryptography to provide some security. And the idea is twofold. The first is it is game-based, where we talk about indistinguishability. So if we have a protocol, then we run the protocol as it's supposed to be, and we collect the output, which we call the real part. And then we take the protocol and we run it, but we exchange some until every important mathematical step by just doing some random sampling, which is the random part, which is the semantic security that was presented earlier. So we take the protocol, we run it properly, we run it in a random fashion, and then we have two outputs. And now I give them to an attacker and I ask them to distinguish them. And the idea is that this is not possible. And then the second idea of SSProve, state separation proofs, is that they're reduction-based, which is also typical in cryptography. So we reduce the security of the protocol to some usually mathematical assumptions below. For example, El-Gamal is based on Diffie-Hellman, RSA is based on the factoring of big numbers, and so on. And now SSProve brings this to the COC theorem prover. And here, why do we need this extra library? Because we talk about probabilities, and we talk about state, which this library provides, because it's not given in the book yet. A little intuition to how SSProve works. So we have this notion of packages. You see on the left, you have X and Y going into a package. They're called export. And then on the right is Z going out as an import. On the top right, you see some pseudocode of how this package would be implemented. And now on the bottom right, we have two important definitions. So a distinguisher is the package with the export run. So it sort of initiates a game. And a game is a package with no import. So if you take these packages and we combine them to the big protocol, so we divide the bigger protocol into these packages, and then the distinguisher sort of starts playing the game by calling the run export. And now we have the most important definition probably is the distinguisher advantage. And as always against the game pair, because we have a game, the real game, and then we have this random or ideal game. And you see the definition, it's a bit technical, so I'll just give you the idea. What we want is that the attacker has no idea of how to distinguish those two objects or measure them. And if the best thing that he can do is to flip a coin, which is a 50-50 chance, then here the advantage is 0.5 minus 0.5, so it's exactly 0. And if the attacker knows exactly which one is which, then, for example, on the left-hand side, he says that game 1 is true, and he will always say that because it is true. So he has a probability of 1 minus a probability of 0, because he knows the other one is never true, and he always wins. Now we apply this to remote attestation, and what is the current state? So we implemented signatures as the primitives and as a protocol. We did the same with remote attestation. Now you may ask why signatures? Because if you look at remote attestation from a protocol perspective, it is essentially a signature. And so we mostly reason about the security of signatures. And you see our main theorem here. You can very kindly ignore the first 5 lines, because again, our protocol is a sort of a combination of packages, and we have to teach SSProve that our packages are valid, or we have to give them hints. And you see the last 4 lines is the important part, where we say the advantage that we've just defined of the ideal attestation part and the real attestation part, and any given attacker A. This is smaller or equal to the advantage of a singular setting just with a signature. And what that means is, if an attacker is able to break the attestation, which means this advantage here is very high, you know it's always limited by the advantage of breaking the underlying signature. And now this is where the second lemma comes into play. If we now can prove, given a specific signature, that this is just not able, cannot distinguish the real and ideal part of the signature, then the underlying advantage for the remote attestation is very small. And this last part is our future work, because so far these signatures haven't been implemented mathematically. And in the TPM, this is RSA signatures, and also the ECDSA, the digital signature, which is the last part. And then we made, I hope, a significant step. Thank you.
Okay, so I have a good question before I ask the rest. On slide, I think it's on slide just last time. So you mentioned primitives and protocol. I was wondering what's like I understand like signature is also primitive, but how does it mention the protocol? Is it that one part is science and the other one is seed? And this is what you verify that let's say the integrity of the message was protected. Is it something like this? Like I'm trying to understand what is the protocol when you say signatures.
No, I might have a different annotation to primitives. So for a signature, our primitives is you have a key generation, and you have a functionality that signs, and then you have a functionality that verifies the signature. This is our primitives. Of course, you can call a signature itself the perfect primitive, but I meant the primitives of a signature scheme, and then if you combine those into a protocol, you get what you actually consider a signature protocol. But the reasoning so far is only on the primitives.
Okay, nice. So this reminds me kind of a discussion that we had in the CCP attestation SIG, and there, like somebody asked me that, okay, so this remote attestation may be a protocol, so it's only doing signatures and something like that. So is it really a protocol? So there was a long debate on that. So how do we define a protocol? So and even in basic books, we know that even if it's sending some message, it has something to do with cryptography, we call it a cryptographic protocol. But I wonder, like, is there any standard distinction between when we say it's primitive and it's a protocol? I understand you're working more on the kind of the computation side, but just wondering if you have any thoughts in general, if there is any kind of distinction between the two that is kind of considered standard or maybe more understandable for community which is not from form, I think something like that.
Unfortunately not. It's a very good question. It's a bit hard to answer for me. So if you look at remote attestation as on this slides, clearly from a person with triple background, it looks like a protocol. But I think what you are going at is that this is just a primitive, like a signature primitive, and then the protocol is more of a bigger thing, like TLS, for example. Is that where you're going at?
Yeah, it's trying to distinguish between the two products of every unit within the offense of any that's the question. Yeah, George.
Yeah, so I have a question on the last slide as well. Just wanted to make, like, what do you mean by signature as a community? Because for me, I think the signature, I think, okay, you have a signature or a state, whatever. But how, like, do you define a signature as it's an ideal signature and we don't care how it's implemented and that's how we reason about it? Or is there algorithm signature that's specific?
Yeah, this is what I meant by part of the signature work. So right now, my signing function is just an abstract function that just gives me something of type signature. But the next step is to actually mathematically implement those. This is RSA and CTSA.
Okay, thanks.
Okay, any other final questions? Okay, then let's thanks the final speaker. Thanks.